DART stands for Double Asteroid Redirection Test. It launched in November of 2021 from Vandenberg Space Force Base. And it took a little bit less than a year to reach the target asteroid, which is named Didymos. Didymos is a binary asteroid. That means it's an asteroid with its own little secondary asteroid. You can think of it like its own little moon orbiting it. So it's two asteroids orbiting around each other as they both go around the sun, just like the Earth does. And the DART spacecraft intercepted the smaller component of that binary system, which is named Dimorphos, on September 26th of 2022. It was going about 14,000 miles per hour relative to Dimorphos when it hit. Dimorphos is about 160 meters wide. In Didymos, the parent body is about 780 meters wide, so it's quite a bit bigger. And so the goal of the mission was to make a small but very measurable change in the motion of Dimorphos as it orbits around Didymos. And by measuring that change in Dimorphos' orbit, we could test and validate several key aspects of that asteroid deflection technique, which is called kinetic impact. And it involves basically crashing a spacecraft into the asteroid to change the asteroid's momentum, which changes the asteroid's orbit. It speeds it up or slows it down a little bit. And if it's done far enough in advance, that can be enough to prevent the asteroid from hitting the Earth. And so in the case of DART, we wanted to see, well, how much can we change Dimorphos' orbit? How well does the change match our predictions? And how much of that change was due to asteroid material that was ejected out of the crater that DART's impact made on Dimorphos. That's one of the big questions, the big unknowns in the field of asteroid deflection study, was how much the ejected material would contribute to changing the asteroid's orbit. And we got our first hard data characterizing that behavior from the DART mission. Most of the ejected material came out of the side of the asteroid that we hit, which is what we expected. It wasn't evident that any material got knocked off the opposite side of the asteroid. It seems like all the ejected material was coming out of the crater that the spacecraft impact created on the side of the asteroid that was hit. It was a lot of ejecta, certainly on the higher end of what our models were predicting. And we slowed the asteroid down rather than speeding it up. So we slowed it down by about 2.7 millimeters per second, which is a very, very small change in velocity. But it was enough to change the period of the asteroid's orbit, slow it down by about 33 minutes. So the original orbit period was just under 12 hours, and we were able to reduce its orbit period by about 33 minutes, which was very detectable in our planetary radar system, which is the Goldstone planetary radar, as well as all the telescopes, all the optical telescopes that we use to track the asteroid.